Oh, I can see here. Should I like it? I make a like for you.
It's up to you, as you wish, right? I'm not sure whether you share this today webinar with your team group or with your team or anyone.
It's a holiday season here in Denmark.
Oh,
It's called Påske,
oh,
so everyone is
oh,
is gone basically.
oh,
I can
I
share
know.
with
Oh,
them, but no one would join, I don't think.
okay. Okay, no. Yeah, I just forgot. Yes, it's holidays in Europe. I think mainly in Europe. Yes. Okay, I think we can start. I will start myself. I think the attendees are free to join the webinar as they wish. Okay. Okay. Hello. Good morning. Good afternoon. Good evening to everyone wherever they are attending this online meeting. I am Ali Rahman, hosting the Pavement webinar series at Southwest Yaletown University's an initiative aimed at enriching our academic environment by inviting distinguished and international scholars, research, and experts across various domains of pavement engineering to share their insights and expertise as a speaker in this webinar series. And in fact, the core objective of this initiative is to expose our students to the forefront and our also researchers and faculty alike to the forefront of research and the latest advancement in pavement materials and structure through this pavement webinar series. Today, we have the third episode of this pavement webinar series with the title of Digital Twins for Civil Infrastructure with Application to Pavements. And our today speaker is Dr. Eyal Levenberg from Technical University of Denmark. Dr. Levenberg has been involved in pavement engineering for nearly 30 years, including 6 years and an Air Force engineer, and nearly 2 decades as a self-employed pavement consultant. Eyal holds a PhD in civil engineering from the Technion IIT. Dr. Levenberg started his academic journey in 2009 and is currently an associate professor, head of studies, and head of section at DTU Sustain. And his research centers around pavement mechanics, focusing on the advanced interpretation of sensor readings for condition assessment of pavement systems. And thus far, till now, he has authored or co-authored over nearly 80 paper-reviewed scientific publications. And also his lecture notes on pavement mechanics were recently published on Amazon. And also his spreadsheet-based layered elastic program, Eyal, has been also downloaded and utilized by hundreds of engineers and students worldwide. So thank you so much, Eyal, for accepting my invitation. It's a privilege to have you today in this webinar. And before starting the presentation, I just want to mention that this session is an interactive session where during presentation or after presentation, you can raise your hands and just turn on your mic and ask your question, and or whether you can type your question in the chat box, so that I will be happy to read the question for Eyal, and he will answer to your question. I hope you will have a very fruitful online presentation today. I hope all attendees, especially the students, can actively participate during this session, this interactive session, so that they get more knowledge regarding the digital twins application, especially in civil engineering and pavement engineering specifically. With that, I give the floor to Eyal, and yes, so yes, I'll let Eyal start. Yeah.
Yeah.
Thank you, Eyal. Yes. Yeah, back to you.
Yeah, thanks for the invitation. It's really a privilege, and also I think it's a good chance for us to share what we do in DTU and get some feedback. This is the most important part, at least for me. So I thought I'll make a short presentation so we can have a longer discussion. That would be the ideal situation. And I hope you can hear me. I can try to share my screen.
Yes, we can hear you, Eyal, and also we can see your presentation, your screen. Yes, great.
Excellent. So I'll start, as I said, it's a short one, just to get the discussion, because this is a relatively new field within civil engineering. The official title, as you said, Ali, is Digital Twins for Civil Infrastructure with Application to Pavements. I'll start with the definition. What is a digital twin for infrastructure? We started looking at this some years ago and found out that there are many competing definitions of a digital twin, especially in the field of civil engineering. So we decided to come up with something that we can agree with. And what we came up with is that the digital twin for infrastructure is a duplicate computational model of a sensed infrastructure, and with continuous updating of model parameters and model formulation. And the updating is based on sensor readings. I'll just read this again. Maybe I can make also my pointer more visible. So it's a duplicate computational model of a sense infrastructure. Here, the duplicate computational model is something that we are used to doing in the past, semi-analytical models or finite element models. But the point here is that the infrastructure itself has sensors buried into it. And this is the most important part that makes the digital twin. There is a continuous updating of the computational model. The model parameters and also the model formulation are continuously assessed and updated. And the updating is based on the readings from the sensors that are in the infrastructure. just to clarify better what I just had in words, I'll try to do this graphically. So imagine the real or physical domain, and this is a timeline, and I'm having here two time instances, ti and ti plus 1, so two consecutive time instances. And here is the infrastructure represented by a square, and here is the environment in which it performs. Environment is not necessarily only environmental conditions like weather, wind, solar radiation, but it could also be the loads that are applied by the users over the infrastructure. The infrastructure you can think of as a road, or as a bridge, or as a building. The colors here represent the state of the infrastructure and the state of the environment. And after a bit of time has passed, I have the infrastructure here drawn with slightly different colors to represent the fact that something has changed. And also the environment, of course, changes. Some loads are gone, some new loads arrive, or the sun is shining, or the wind is blowing or not. So this is two time instances for the real domain. And within the infrastructure and within the environment, we imagine to have some sensors. So the sensors in the infrastructure are measuring vibrations, stresses, strains at certain locations within the infrastructure, and the sensors in the environment are measuring the environmental conditions, if this is a weather station or some weigh-in-motion system. Of course, in between the two time instances, the readings are different, and this is what the color indicates inside the sensors, that the data coming from the sensors is different. Here's the digital domain. We have the infrastructure digitalized, and we have the environmental conditions measured by the environmental sensors applied over the computational model of the infrastructure. So these are kind of boundary conditions or initial conditions, if you like. And we have the same as the environmental conditions change. We use the environmental sensors, and we take their data and apply it over the computational model of the infrastructure. We can also, in the computational model, produce virtual sensors that are located in the computational model exactly where they are located in the physical infrastructure. So if something happened to our infrastructure or between the two time instances, if the properties changed, for example, an element lost its modulus, or if there's a change in the structure, something broke, or something had been covered by a layer of snow, for example, if something has changed, then we need to update our model parameters or even the formulation of our model. And this is how the digital twin concept works, because we are following reality within our computational model. I would like to say something about parameter updating. This is the general scheme for parameter updating. We have the computational model here with a virtual sensor, and we have the current set of parameters, and we have the environment operating over the computational model coming from measurements. And then we generate the digital sensor readings and compare them with the physical sensor readings. And if we see any discrepancy, we perform an optimization process, update the parameters, and input a new set of parameters. And this is going continuously. Some years ago, I had a master student. Her name was Lucia Barisic, and we worked on a digital twin for an asphalt road. And this process of updating was done in her master project using controller theory. So here's an application example. The application example has been published in 2022. The title is A Thermal Digital Twin for Condition Monitoring of Asphalt Roads. So here we are focusing on twinning the thermal state of a pavement. We used data from Highways England. I'll show what we had. This is a cross-section of a pavement, a highway pavement. This is the pavement surface where the loads are applied. This is the asphalt concrete, and here's the base, and below, further down, are the other layers. And we took 3 temperature sensors that were buried in the pavement and recording for several years. And each of them was recording temperature every 10 or 15 minutes. And we had access to the measurements, as I said, over several years. We made a digital twin for that part of the pavement, the upper part. The temperature T1 is the top temperature sensor. That would be our thermal boundary. And the temperature sensor 3 would be the lower thermal boundary. So thinking of the pavement as a very wide, it's enough for us to use a one-dimensional heat conduction formulation. So the top part of the pavement, whatever the temperature sensor was reading, is treated as a boundary condition to the model, and whatever the temperature sensor at location 3, which was about 30 centimeters below the surface, was taken as another thermal boundary. And the governing equation that controls the heat transfer between the top and the bottom was the normal heat transfer formulation. Here you can see alpha as the single parameter here, which is the thermal diffusivity. For those of you who do not work in this field, thermal diffusivity is basically the conductivity, the thermal conductivity of the medium divided by the density and by the specific heat capacity. So we have an assumed diffusivity for the medium, that is the material between the top of the pavement and a depth of 30 centimeters. And then we could generate readings from a virtual sensor that would be located here, where actually we had a sensor measuring. So we could compare the model temperature predictions with the real measurements predictions. And then if there was any mistake or discrepancy between them, we could have updated, and this is what we did. We updated our diffusivity and ran the model again. And this was done continuously using the data over several years. So here are some results. You have here the thermal diffusivity on the ordinate, and here you have 5 years of data on the abscissa, and you can see here 2 highway sections that were analyzed in this way. The first one, the thermal diffusivity was not very stable over time, and the other one, the thermal diffusivity was very much more smooth and stable over time. So what can change the diffusivity? So we had a look at this, and we assume that if the surface of the pavement is not in good condition, for example, if you have cracking or open construction joints or porous surface, then over time water can enter or evaporate, and that would change the medium thermal properties. If you have the same thermal diffusivity along several years, as you see here with the green line, it would say to us that there are no cracks or very little cracks, and the surface is not porous and nothing can enter and leave, and that is why the thermal properties are more or less stable. So we took some pictures. You can see that the pictures linked with the more noisy diffusivity, they clearly show that the construction joints are open, the surface is porous, there's raveling and stripping, there are also some cracks, and this has been the situation. And the other part of the highway where we had a section where the diffusivity did not change, we could see that the surface was in very good condition. Construction joints were closed, the surface looked watertight, and there was no raveling and stripping. So here's what a thermal digital twin can tell us without being physically in the field, just based on updating the parameters. Here's the potential utility for digital twins. The first one is know your structure, because you can get information from your twin on unsensed locations. So I showed you how the computational model can generate results where sensors are. I call them virtual sensors, but in fact, the computational model can give us information about every location in the structure, not just where the sensors are. So this is the first point here. The second point is that you can do condition monitoring, as I just showed you, based on analysis of how parameters are changing. And this can lead to support in maintenance because you can be reactive in your activities if you have your digital twin running continuously, and you can also see some trends and prepare. So these are predictive decisions related to maintenance. Another idea to use for using digital twins is to explore hypothetical scenarios. I mean, if we have a twin and it is representing reality, we can torture the twin and expose it to different conditions just to see how things are going to behave. So here I have some ideas. For example, exposing the twin to extreme environment. It could be extreme in terms of weather. It could be extreme in terms of loading. We can try to change some of the components with non-standard materials and assess the behavior in the computer. And we can also play around with failing certain components and observe the response of the twin. And since the twin is very closely linked with the reality, then these results would I would deem them more reliable. There's also this idea of closing the loop with design and construction. Many times we have our own designs, and then the construction crew builds the structure or the infrastructure, and then that's it. The designer never gets feedback from his design, and you cannot really check if your assumptions are fulfilled or not. So this is another potential utility for digital twins, is to provide the feedback on design and construction. Some fine points just to close the topic or the presentation. There's something called twinness level. Even biological twins are not 100% identical. And in our case, when we talk about the digital twins for infrastructure, we have to somehow define how good is our twinness level. And that depends, of course, on how good is the modeling, your limitations in terms of sensing. I mean, all our sensors are not perfect. And of course, we have a limited amount of sensors that we can bury in the infrastructure. And then also the updating frequency. Are we updating our model every millisecond, every second, or every 10 minutes, or every year? The parameter updating is currently the most common for digital twins. The formulation updating, have not seen anyone that is revisiting the formulation during the digital twin process. And I think this deserves a bit more research, because it's not that easy to decide that your structure changed to the level that requires a new formulation. But this is quite easy to imagine. Let's say we assume a layered theory for our pavement, and then there's a crack somewhere. Suddenly the layers are no longer extending to all directions and are continuous. We have to introduce discontinuities. So this is what I mean by formulation updating. Another idea, just to give you some intuition, the thermal model that I showed you, if something changed in the material, for example, there is a frost inside the pores, so the water enters and then freezes. So that the thermal model that I used is no longer valid if you have a change of phase in the water. So that requires another element in the differential equation, and that means updating the model. Currently, I can see two types of digital twins. The first type I would name as a child twin. If you are twinning a project that is under construction, this is all the BIM ideas, or building information modeling ideas, where you can see that there's a twinning happening for the actual construction of the infrastructure. And what I showed you and what I'm more focused on is adult twinning, where we have a infrastructure that is under operation, and the digital twin has the aim of twinning the operation phase. Thank you very much, and I'm hoping to hear some questions, ideas, or suggestions.
Well, thank you so much, Eyal, really, for your insightful presentation. Very interesting, and the really digital twins. I believe that in the coming years will have a more application with especially digitalization, automation, and everything that in the pavement engineering we are involving. We are working this. I think digital is something very useful tool. So among the audience, if anyone has any question, please raise your hand directly and ask Eyal. No question?
Yeah, give it time. Maybe
Okay.
people are sometimes shy to start.
Yes, sure. Let me, yes, sure. Yeah, until someone, they can wait. I can ask you, maybe I have one or two couple of questions.
Sure.
Yeah, it was very interesting, the presentation. And my first question was related to the project which you modeled a pavement, the thermal behavior of the model, and you define a medium, as you mentioned, the upper boundary and the lower boundary, and then there was the middle sensor that, in fact, using the digital twinning to predict its in fact the temperature or variation of the pavement in that point. As you mentioned, it is possible to extend that prediction to any point in that in that medium, for example, in the pavement structure. So my question is that, first of all, why for upper boundary and for lower boundary sensors, no prediction or no have been done? I mean, you just focused on the middles, the sensor, the second one, which was in the middle. What was the reason that upper and lower sensor were not predicted or was not taken into consideration for modeling?
Well, they are used as inputs to the model. If you would like to predict the temperature in a pavement, then you need information about wind and solar radiation and cloudiness and the reflectivity of the surface. It is possible to do that, but if you have a sensor that is buried very close to the surface, not exposed to the sun, let's say 1 centimeter below the surface or half a centimeter, then the temperature at that level is already known, so there's no prediction needed. We were interested to find out the mechanical conditions, condition of the pavement layers using temperature sensors. This is a completely new, let's say, paradigm where temperature readings can tell you something about the mechanical condition. The reason I'm focusing on temperature is because it's quite cheap to measure temperature. Cheap in the sense that the thermal sensors are extremely cheap themselves, but also the electronics that is needed to drive the readings is very cheap. And you also do not need to collect many readings every second. It's enough to take a reading once every 10 minutes, and then you know that temperature doesn't change very quickly. The ideas of instrumenting pavements with vibration sensors or velocity sensors, geophones, or some other sensors that require high acquisition rates. These ideas, I cannot see them currently being deployed on a wide scale because the energy demands are high, meaning you need a cable to reach the sensors in order to give it the energy it needs, but also take out the data. And I would like a future where we have sensors that are wireless, that you can just embed them, think of them as being encapsulated like in aggregates, so that you can tell a contractor 5% of your aggregates are smart aggregates, they are sensors, they have inside batteries and wireless communication abilities. I don't see that happening in other types of sensors except temperature. Temperature, I can imagine being measured across wide areas tomorrow, to be honest. There is no limitation. Batteries would last for years. So
great. Okay,
yeah,
thank
so
you.
That's
thank
the
you
concept.
for you. Yeah, for your reply. And also, my another question is about which platform or software have been used for modeling or twinning or digital modeling of the structure. Is it any specific software or program, or just need to programming, coding, or?
Yeah, so that once you have the differential equation that governs your structure or integral equation, we like to write our own code in DTU and also share our own codes. So you can find codes from my previous students placed on GitHub.
Okay. Great.
Yeah. There was a question
Okay,
in the
great.
chat I could see. Someone asked.
Yes, someone asked. Yes, okay, yeah, Hadith was asking, what types of data are necessary for creating an effective digital twin for pavement infrastructure?
It depends what is the twinning interest. We cannot twin reality completely. We have to decide what are we focusing on. So when you focus on a thermal state, then you use data from temperature sensors. If you like to focus on strain state or stress state, I mean, you decide what you would like to focus on. And based on that, the data comes naturally. At least the data needs. I don't know if it is very easy to measure outdoors everything. I see the problem with the sensor world. There are not many sensors that are designed for wireless communication, and there are not many sensors that can last many years on a battery. So it's difficult for me to see how you take 100 or 200 kilometer highway, bury sensors in it, and they would work for 10, 15 years and communicate wirelessly the results. In fact, wireless communication does not work well underground. So if you bury a sensor, it's very hard to hear what it wants to say. You know, when miners are trapped underground, sometimes the rescue teams, they are racing to get an old-fashioned telephone cable to them in order to have some communication line, because wireless signal does not work well underground. So this is another issue that the sensor world needs to help us, the pavement engineers or civil engineers. How do we get data out from below the surface when we are surrounded by a medium that is basically soil or aggregates? Yeah.
Okay, great, thank you. Okay, I have one or more two questions from my side, Eyal. Yes, as you mentioned, digital twin has no limitation, but although in the application, still it is in the beginning steps. I want to know if there was any experience have you done in terms of evaluation of subsurface condition? For example, some failures. For example, one of the what I am doing or researching is interlayer bonding between pavement layers, which is one of the failure types in the pavement that it cannot be seen unless it shows on the secondary distresses such as top-down cracking or bottom-up cracking. So is it possible, do you think, that we can monitor or predict the interlayer bonding degradation in the pavement structure? Is it possible? Do you think or what might information or data would be necessary to collect or for modeling the interlayer bonding?
Well, if you're talking about using temperature information to predict interlayer bonding conditions, my assumption would be that there has to be an influence on the thermal conductivity if the layers are bonded well or debonded. If you have a debonding, the thermal conductivity has to be influenced through the layers. Currently, in our models, we like to think of a full thermal link between layers. So if one is hot, the layer below is affected as if they are touching perfectly. But that part can be made imperfect in the thermal analysis, and maybe that can give you something about the bonding. So you can even see that without a mechanical load, just based on the fact that the heat is not conducted as well as it used to. So that's an idea. Of course, if you have sensors just above and just below an interface that measures some kind of a strain of sorts, then if there is a debonding, these would be showing. But then again, you cannot sense everywhere. And I don't know how problematic is the debonding. Is it only where the traffic is, or is it the entire layer? So there is a challenge here. But yeah, maybe through temperatures.
Okay, that's great. Yeah, I think maybe it could be a very good topic for maybe some research collaboration there, hopefully.
Yeah,
In
I can
future. That would be
I can
very
mention
interesting.
this is a different thing. Not far from my office, there is relatively not far. There is Dynatest headquarters, where the company that makes falling weight deflectometers. And recently we worked together on an idea to add an extra geophone on the FWD plate. You know, currently all FWDs in the world, they have a geophone in the center of the loading plate and a geophone outside the loading plate at an offset of 20 centimeters or more. We added a sensor on the plate itself by making a small drill hole through the plate and placing another geophone at an offset of 10 centimeters. So having two sensors very close gave us the ability to understand better thin layers. Back calculation was always limited by the spacing between the sensors. And now that the spacing is smaller, it can be done also for thinner layers. So it could be an interesting idea to look at debonding. Can that be identified with this new geophone or other geophone? Yeah, something for next year, B.
Yeah. Oh, great,
Yeah.
great. Okay. Any question from among audience? Anyone? Okay.
Maybe I can add something. I shared with you the presentation slides, and you can share them with everyone that is interested in the webinar.
Yes, sure.
And also maybe you can say, is anyone working on digital twins for pavements or for infrastructure on your side?
Mm-hmm.
Do you know if anyone is doing that?
No. At least in my group or highway engineering group, I don't know. Maybe perhaps in other department we have faculty or colleagues who are working on that. But in highway engineering, as long as I know, no one is working on digital twin, right? And okay, just my last question that I forgot to ask you. On your slide 10 of your presentation, which you show the prediction results of the temperature sensor for two highway case, and what you show the evolution was the prediction models. Yes, what model predicted over the years. Am I right, or it was what happened?
The thermal diffusivity as calculated inside the digital twin in order for the measured and computed temperatures to match. So by matching the T2, the second temperature sensor, we were able to find out what is the real diffusivity in the field without measuring it in the field, just based on temperature information.
So okay, so do you have? I want to know if the data for the T2 on the field is also available for you.
Yeah.
So if I want to know how really the results match together. I mean the field data and the digital twin data, how they are fit together or match together really,
They are matched. There's one parameter to adjust, which is the diffusivity, and there's one target to match, which is the temperature at the T2 sensor. So what we did is every week of data, we matched it. So it is matching as best as the model can. If you're asking about the matching ability, it's almost perfect.
Right.
It's almost perfect because we are doing that. This is an artificial match. It's not a prediction. We are making it to match, and then we get the diffusivity out. So yes, extremely close. I mean, you can remember. You need to remember that sensors are also not perfect.
Right.
Yeah, and the model itself is not perfect. There are some assumptions there, but yes, it's almost perfect match because we are making it to match. We are forcing it to match, to be honest. Yeah.
Okay, very great. Okay, thank you so much. I learned a lot really from your, and also as I said, some new idea also came to my mind also that it will be help hopefully for future research. I hope there would be a chance for both of us to find some research to collaboration hopefully in this area.
The delamination is an interesting question. It's are you modeling it with the finite elements, or how are you dealing with delamination?
Actually, the delamination debonding, we are doing a range of techniques from lab experiments We have already developed, because there are no, OSHTO has an international standard direct shear testing, but I also develop in our lab 1 or 2, 3 setup for interlayer debonding in shear, in fact, shear modding. And this is one, of course, the one approach, both using a cyclic loading and a static loading or monotonic loading, because of course under any case they have their own different indices to evaluate interlayer bonding. And then of course another thing is the modeling, of course the simulation using Abacus or ANSYS or any modeling software, who can of course be giving more factors, parameters, variables, so we can get more results. And what actually we are now focusing in my group, and what I am doing, using an NDT, non-destructive testing, especially with focus on GPR, ground penetration radar. And now we have some idea, and we are now of course using such as techniques like deep learning or machine learning to and also signal processing to evaluate subsurface debonding, delamination. So these are some works that is on the progress. But in terms of experiments and numerical modeling and also data science, machine learning, we already done a lot in that. We have publication, and yeah, this is the area that we are now moving for, is now progressing.
Yeah, it's very interesting. Recently, we had a project about grid reinforcement in asphalt. Grid reinforcement there was always a concern that it would be affecting the bonding between layers when you insert a grid. So we did some lab tests, also cyclic shear, things like that. And yes, you could say that it affects the bonding, but it depends how much, because the overall reinforcement effect is not necessarily gone if you have some drop in the bonding level. Yeah. And we work with Dresden. The University of Dresden, they have developed their own shear test for interlayer bond, and they helped us with the tests. Yes, it's a cyclic, and the bond itself is characterized almost like a viscoelastic spring. So it's not a single parameter. It's more like a master curve, you can say, depending on the rate of or the quickness of how you shear it. So it's the frequency dependent entity.
Exactly.
But all small strains. We never reached a failure. It was all small strain characterization of the bond. Yeah.
It was cyclic. So how many cycles?
Yes. It's many cycles, and under different temperature conditions, to make some kind of a master curve for the bond, for the interlayer bond.
Oh, okay.
Yeah.
Okay.
Yes.
So whether the test, it failed. At the end, the bonding happened.
No. It's just to characterize the level of bond under service before failure, because the strains in pavements are quite small, I would say. Yeah.
Right. That is true. Well, that's great. Very interesting. Yeah.
Yes.
Do you have some results from that, or some published? It is already some dissemination.
It's published. Yes, it's published.
Okay.
Yes,
okay. Great.
Everything is published. And I think Dresden themselves published some work about their own device and the measurements that they were collecting over the years. So yes, I think you can find it on Google Scholar. It's out.
Okay, great. Yeah,
but I can share with you if you're interested.
No yeah, thank you so much. Thank you, Eyal. Okay, yeah, very nice chatting and conversation. Any other question among audience? No one? Yes. Okay, so yeah, it seems we have no more questions.
It's either everything clear or everything is unclear. Then we don't have any feedback.
Yeah, this is perhaps I guess most probably the digital twin was a new concept for them, and for maybe they are just want to digest the concept, and then but
yes, it is an emerging concept in civil engineering in general.
Yes.
And as I said, it starts with child twins, because the construction people are digitalizing the construction process. And yes, after everything is constructed, then you go to an adult twin and start looking at operation and maintenance. So yes, I would say this is the future of civil engineering, to be honest. Sensors, signal analysis, and deep understanding of mechanics and thermal.
Great. Oh, great. Thank you so much, Eyal. Really very nice presentation, very insightful. I myself learn a lot, and I hope other audience, students also get some knowledge, information about the digital thing, hopefully to maybe some idea for their future, for their research can be, of course, why not? Yeah. Okay. I think, yeah, with that, we can wrap up our today webinar. Again, thank you, Eyal, for accepting my invitation for this really insightful presentation. I hope we could have, whether when you have a time, we are very welcome to have you again in similar webinars if you have time. I know your schedule is also, you have your own schedule, is very packed, and so, but anyway, anytime you have time, I will be very welcome to anyway reach out to you in case if for future webinar. Okay.
Yes.
Yeah.
Thank you.
I think yeah, we are getting the, no, it's just, yeah, there are okay, the comments are also appreciated. Thank you so much for sharing your knowledge and expertise, sir. We are really grateful. I'd like to ask if there is any possibility of using this concept to simulate pavement cracks. Suraj is asking.
Yeah, I mean, if there are new cracks in the pavement, it would affect the thermal properties of the layer on a smeared sense, on an average sense. If you have a lot of small cracks, yeah, so it is indirectly measuring cracking. If you want to measure directly cracking, then it's a question of which cracks. The ones that are starting at the top and making their way down, then you can see them. The ones that are in the structure that are working their way up, it's not possible to see them. So then you need some indirect ways, like GPR or thermal sensing, or maybe mechanical loading. We have been looking at the TSD and the Raptor, the two machines that are driving and measuring at the same time. They are both developed and produced in Denmark. Also, not so far from the university. And yeah, it's a challenge to drive 80 kilometers per hour and also see movements because of your self-weight at the level of microns. But this is, we are getting close to this ability with the new lasers and electronics.
Right.
Yeah,
That's
I
right.
would say,
True. This
yes,
is
our field is being pushed to look more into signal analysis and sensing, and I think this is a new civil engineer.
Right.
Yeah.
Exactly.
Civil engineering
Completely agree.
4.0. Yeah.
Yes.
Machine
True.
learning you mentioned also.
Yes. Yes, this is some. Actually, also we in our lab we have one of the colleagues who are working on high-speed 3D laser scanning of road surface. Yes, and Dr. Alan Jung also. He's also. We have several the vehicles who are with mounted 3D laser scanners, both which are tested on railway and also on highway pavements. So we are very good results and very good advancement also happen in that site and that area. And as you mentioned, these are really the future of civil engineers, and especially for us pavement engineers that are really pushing the boundaries and really makes our work more easier.
Yeah, we need just to find an alternative material to bitumen so we can detach from the oil industry. And this is also, there's a push from the European Union and also the Danish government to look for alternatives to bitumen. Yeah.
Right.
So
Yeah,
we
that
may
is true.
need
Exactly.
to develop new mechanics for new materials. I don't know if if the findings of this effort would be identical to bitumen. I expect not. We will have new, you can say, damage modes and new sensitivities. And I think this is why it's important to focus on the basics in your education. Get basic knowledge that you can adapt all along the way as you know, technologies change and progress.
Exactly. And I think since you work, I mean, basically pavement mechanics, this is, I know that is a really matter of concern for you. As you mentioned, these new developments happen, new materials, and this is something maybe the traditional equation or principle should be transferred to new ones. And
Yes,
yes, exactly. This
it
is
will.
something
It
that,
will. Yeah.
yes, it will be happen. Okay. Okay, very great, very great. Thank you again so much, Eli. Sorry, uh,
Yeah. Yeah.
Eyal, and for your presentation. And so if no more questions from everyone, we can wrap up our presentation today. Thanks for your time. Thank you everyone for joining this webinar. And we are hopefully looking forward to meeting you in our future and upcoming webinars. Please stay tuned. Thank you everyone and have a nice day. Thank you,
Bye bye.
Eyal. Bye-bye.
Thank you.
Bye-bye. Have a nice day.